Now we're on June 16th, 2010. Dupree, South Dakota had several tornadoes around it. And for starters, here's your mid-level 500 millibar trough at 7 p.m. that day. See the dip here. And the wind, now notice on this setup, these winds are sort of weak. I'm just kind of showing a setup that can work with weaker winds, especially mid-levels. A lot of people want 40 or more knots, you know. But as you can see, Dupree happens up in here. And really, you only have 20 knots southwest, 25 knots here. So it's pretty weak mid-levels. And then you'll have a front, a warm front's coming up here. You'll have a surface low that deepens in here. So the play was along the warm front. The biggest area outlooked was out in here, but the warm front worked out very well. This area didn't really even work out. But there'll be a trough. You can see it here, the mid-level, but there'll be a cold front come down behind that one. And as it sags, it'll slow up. And then the next system comes out and the low deepens and it turns back north as a warm front. You'll see it on satellite and surface right through here. Here's the surface map that morning at 10 a.m. You can see if you look, you got southeast, south-southeast winds here, and they bump into more easterly here. They're even more easterly here. You can see right there, south, and bam, you turned it to almost east. So you can tell the warm front is right about through here somewhere. And now you can look at the surface pressures too. They never got real low, but you can tell as the day went on, it's steepening out here. You can see this is, again, if it's a 0, starts with a 0, you got to put a 10 in front of it. So it's 1007.2 millibars, not real low. And then if I go to 6 p.m., you can see now it's down to 999.9 millibar. So the surface low is deepening out here. That warm front has lifted. You see this area went to southeast and then it hits more easterly here, 90 degrees, and there in Norfolk. But that warm front's now going through here, and you'll see it on satellite really clearly. The play ends up right about in here, so you got very backed low-level flow, almost easterly, and then the low-level jet gets pretty good too. So you go from that to those mid-levels that were only 20 knots, but they're going this way. You have this front going this way. So as that front, a lot of them, storms were trying to lift over that front. They weren't doing so well. But then once one anchored and turned on that front, it was, again, that even if it's weak, it was turned enough that it helped the storm relative flow at that height. That storm really got rotating. And then there was good enough flow aloft. There's pretty good flow aloft. Higher up you'll see to vent it this way, to vent it as it goes east on this boundary. Very slowly. That's the other thing. When your mid-levels are weak, that's kind of your steering height. You can kind of expect a slow-moving storm. And this storm is crazy. I sat in one spot for 2 hours and watched it hardly move at all. Now you'll notice the warm front will be showing up in here as the heating of the day starts acting on it. Start getting the cumulus clouds out here where the mid-level temperatures aren't as warm as over here. You know, the capping layer. You get a little less capping, and the terrain's higher out here too. It helps you're closer to the cap in a way. So the moisture, you just gotta get the moisture back there, and that for sure was back there. You notice cold pocket up here. That's where that upper low was over here. That sent a cold front down here. And as this big upper low come in, it lifts it north, or back north as a warm front. You can see these getting lifted over the front there. But this one is Dupree that just kind of anchors on that warm front. And as I went west, I could start seeing areas that were on radar, just little returns wanting to pop off in the same area. And you could tell that was probably going to be a place to get to. This repeated convergence. Now watch. See, this one lifts past the front, and this one stops, and it's turned on the front. You can see the upper level flow is really, it's venting the top of this storm nicely. If I can pause it. See, the upper level flow is venting both of these pretty good that way. The mid levels just aren't steering them much. They just aren't pushing them much. This one got pushed over. But this one just roots on the warm front and tries to go east with it as it's lifting north. You see the V shape of that. Its anvil's back sharing and then overshooting top would be in there. And just getting vented that way. How much bigger it is. One thing to consider is that during the early season, storms are going to be generally shorter, not as tall. And as the summer seasons come along, storms get taller. So you might want to look at different levels for the vent, the anvil level flow. Like you can see some stuff that might tell you something more. Well, the soundings are the best. They'll tell you the most because they show all the heights. But here's 300 millibar this evening, roughly 30,000 feet. You see 50 knots at Rapid City and then 45 knots over at Aberdeen. You can see it's just probably not above 50 knots through here at 300 millibar. But if you look up a little further above that, at 250 millibar, you can see it's 50 knots, 55 knots. I can't tell, but probably 55 knots. So at least it shows you it's a little stronger just above 300 millibar. And that's pretty good flow, especially for a storm that's not being pushed very fast and it's turned on a boundary. So that storm's turned this way and it's vented that way. So all that rain-cooled air falls away from the updraft base and all the low-level flow comes from over here. If it's low-level flow comes from this way, you'd be getting fed with the updrafts shooting out cold air. You don't want that. So that's why these setups need shear and turning. Here's 700 millibar that morning. And again, this is kind of a good indicator of the cap strength by looking at the 700 millibar temps around 10,000 feet. You see the 10 Celsius. 10's okay in June. You get above there very far and it starts getting harder and harder to get storms. But watch, and again, you got the 700 millibar low like this and your flow is like this, fairly weak, just like the mid-levels at 500 millibar were. But it vects the cap this way, and then the colder air comes in with it. You see on this day, the cap, these warmer temps, like the 10 line you can watch, they kind of go up this way, but they're getting shoved east at the same time, so they just maybe barely clip where the storm is. And they don't get that crazy hot anyway. But you can watch what it does from morning, then again at 7. The 11 and 12 line there. But they're not shoved that hard and they're not that hot. But it's close. It tries to cap it off. You'll see on the sounding. Here's 850 millibar at 7 p.m. that evening. You can see the darker greens are the higher moisture, and then as you go down the lighter greens, you get less moisture. You can see behind that first upper low, it brought down dry air, kind of even off the ground. It got dry down to here, but you can see where it returns. Often it'll return in a smaller channel out to the west, where you have some darker green 12 and 11 Celsius dew points at 850 millibar. And for reference, a 20 degree dew point, or 20 Celsius degree dew point at 850 millibar is extremely high. I've barely seen it over there, where you don't even see a 20 on here right now. It's usually a summer cooling moisture type setup, where it'd be like a 68 degree Fahrenheit dew point up at 6,000 feet. But even these are high for this time of year, and obviously because they're in the darker green colors that they have marked out on here. But anyway, you can see the flow at that level. In this channel here, 30 knots out of the southeast. So you got a weak push from the southwest, not pushing it, bending stronger aloft, bending it, and then it's barely moving and going east, and it's getting fed strongly by these low-level winds. And then the ground level was more like easterly, remember? So it turns to southeasterly, strong at 30 knots at this height. a great setup. You just needed to get a storm out here on that warm front. Another thing worth mentioning is on all these heights, this is above sea level. And it really matters on the low levels, obviously, where you're only talking 6,000 feet on this low-level jet 850 millbar height. But if you're out too far west, you're obviously above that. So these values are given in above sea level. So 850 millbar out here isn't quite as high off the ground as it is out further east, where you're only like 1,000 feet above sea level compared to, I don't know, 3 to 4,000 out here probably. And obviously, if you're near the mountains, you're getting 5,000 feet and above, so you start getting above that level. That's why a lot of those charts you won't see once you get higher, or once you get lower charts, you won't see the readings because they're above that to begin with. I'll try and go over the Rapid City sounding that evening. Rapid City was a little bit southwest of where the storm was, but really not that far, so it works pretty well. This is the actual air the balloon from the Weather Service read as it went up. Again, your temperature lines go this way. So up around 10 or 18,000 feet, 500 millibar is about minus 10 Celsius. Your freezing level is right about here. So this is your temperature line, your dew point line as it goes up. And if you lift the air, that air as it rises, this is the virtual temperature. What's predicted the temperature is going to be of that rising air. Much warmer than the actual air over here. And it crosses up here above 200 millibar, around 12 kilometers. You can tell where about your storm anvil is going to be, how tall. So these winds up here are obviously important. You can look at the winds at the different heights. 500 millibar at Rapid City was at 25 knots from the southwest. You get your low level turning. And a lot of these warm front situations, the low level jet height out here at this 850 millibar or so is a lot stronger than closer to the surface low usually. So if you get a storm out there, it often has a lot better low level shear. And you can see how perhaps 500 millibar is a little misleading if you look 25 knots, but right above it, not very much further up, 45 knots. Pretty good. You wouldn't see that if you were just looking at maps showing each of these individuals levels. You'd see it if you looked at a sounding or a forecast sounding even that morning. But you can see up here 70 knots. That's really good. The storm, obviously, there's a reason why it's tornadoed, and that's it. Great shear, great cape. You're talking 3,500 surface-based cape. And the SIN value, the convective inhibition, you can see it right in there, where your virtual air temperature for a while in this height is cooler than the actual air temperature. That's your convective inhibition. It's only 5, like that's nothing to worry about. Moisture depth right there. That height is good moisture, then it dries off. You want drier air aloft. It's probably worth mentioning and commenting on this again a little bit. You can have the greatest shear in the world. Like this is really good shear, especially over where the storm was, where the low level jet's more like 30 knots or more. And your winds are more easterly even. So where that storm was, think of your surface winds down here being almost easterly and the low level jet being 30 knots instead of 20. Bam, turning up like that. But if your dew point spread between your temperature and your dew point is too big, you got that big temperature dew point depression, then you'll get, as your precip falls into that drier air, it'll evaporate and make a lot of rain-cooled air around your base, which you don't want. You'll have a higher base storm. So some setups, you got the greatest shear in the world, but your moisture is horrible, so it just kind of sucks. And this isn't bad, really. It's when you get the V shape where your dew point line's going more like this, and it's further apart even than this. Then you got that inverted V low level part of your sounding, you end up with a bunch of rain cooled air. But where that storm was, the dew point depressions were a lot closer, so you could probably move this over. The temperature wasn't probably as warm either. So where the storm was, it was really good, which you'll see here in a minute. Here's a quick comparison showing you a worse low-level sounding with the inverted V look to it, where you get the bigger temperature spreads. This is Rapid Cities again. Now watch when I show Midland, Texas from the same day. Now see that, watch the green, the dew point line. It's cooler, drier. You know, the lower temperature. The temperature, the actual air temperature goes higher compared to Rapid City. And the biggest thing to notice is just how far apart they are. Watch the difference in that. That's a lot better than that. Because all this depth of air is a lot drier than the air temperature. Whereas on Rapid City, and then especially it was even closer on this storm east of Rapid City, where the dew point's a lot closer to what the temperature is, so it's really juicy air, not dry like that. That's hot and dry. You don't want to see that inverted V shape on your low level sounding, or you're going to have a lot of evaporative cooling as precip falls into that drier or low level air. And the other thing is, the closer that the dew point is to your temperatures, your low level temperatures, your virtual air will stay warmer longer. So you can see what that would do to your cape. If this was over here, you had a lot more moist air. Your virtual temperature would stay warmer longer. You'd have more cape. And you'd have less convective inhibition too. You'll see that pretty quickly, and you look at soundings very long. That you'll notice, because they start, when that's over here, it starts and goes this way instead of, going like that, barely having any cape here. And I should probably make it clear what exactly that virtual temperature is, so it isn't something that's confusing. I wish the SBC didn't use two ways to calculate it. So if you just imagine one of these, but it starts down here as your actual air temperature, and when it rises, this is what the prediction is that it'll be as it's rising compared to the actual air. This is what the balloon measured was in the air as it went up. This virtual is just what would happen if a front lifted it, or lift aloft lifted that air, and as it rose, it's predicted it's going to be this warm. So the bigger that difference is, the faster and harder it would rise, given everything else is equal. That's why the difference is the CAPE, or the convective available potential energy. Just want to make sure the virtual thing isn't weird. It's just the predicted temperature of the air in the storm that's rising compared to the actual temperature of the air around. And also, real quickly, here's just a quick comparison of the height above sea level deal. Where again, these estimated heights, 850 millibar being 6,000 feet, 700 being 10,000 feet. Those are above sea levels, and then related to pressure too. But if you watch, this is Omaha. See how much lower it is? It's almost down near where 1,000 millibar would be. And watch the difference when I click it over to Rapid Cities, because this is where the balloon's starting, obviously where they let it go. You see how much higher up Rapid Cities sounding starts because they're higher up in terrain. And that capping level is going to be similar as it spreads out across the whole plains. So you generally need less moisture out west because you're already closer up, higher to the capping level, and just how the low levels work. That's one thing to consider, is you can get away with lower dew point air out there. You're already so much closer to the capping, and also the capping can tend to be a little hotter out there. Your 700 temps or wherever it is, it tend to be a little warmer than points to the east because you're your ground level is already so much closer to that level. You don't. It's easier to break it. It's easier to overcome it. As you can see, if that capping spreads out across the plains here, there's a lot more low-level air to warm to be above that level. Whereas if you're out there, it's not as bad because you don't have as much depth. You can gain quite a bit off this radar loop from this day. Rapid City's over here. The radar's right there, but you can watch the first storms. Here's the warm front. The storm's lifting north of it already. This is the Dupree storm that produces a tornado. It stops and stays closer near that warm front roots. Again, remember now, think about this. Your low-level flow along that front was from the east-southeast. The southeast low-level jet, weak, low mid-levels, and stronger flow aloft. So these first storms, I didn't even chase. I just waited down here, seeing which one was going to move to the right. Because moving that way, your storm is not going to ever get organized with this type of flow. Because for starters, the base of the storm is moving towards where it's bending, and right into it. And especially the ones that they're going northwest. Watch, it's going northwest. Tries to go east, dies. This one goes northwest, dies. And if you think about this, imagine your low-level flow is from this way, and the storm's moving away from it. Kind of got zero storm relative inflow because it's moving away from the low-level flow. And what a lot of them are doing, they're just getting the instability and moisture on the north side. The updrafts can be all goofy, and the way the precip's bended from the updraft is kind of in front of it. Or if you're looking at it, your updraft's kind of back here, and your precip's getting bended over here as the storm lifts. Kind of like a left split, you would think about it. And those storms really have to root and turn before they're ever going to organize. So you could sit here and just watch these and wait until one of them turned to the right. The other thing is, even before that happened, you could sit here, and as soon as one would go up in front of the other one, like that one, as soon as that one went up, you knew this storm was toast. As soon as this thing went up, you knew this storm was not a play. It was that simple. Sit here, wait. Oh, that one's probably the one. At least go for that one. Why would this one not work? Your low-level flow, watch. If you got low-level southeast inflow, boom, all this rain-cooled air is going to be blowing back this way. Eventually, this storm is going to ingest the rain-cooled air out of this storm. Real easy to see. All this rain-cooled air is being blown back this way. So if it did turn right, it's just going to ingest, and that's what's killing those. And I'll try and clarify this a little bit. I said that if they're moving north right into where they're raining, it usually doesn't work real good. That's unless you have strong, good inflow. They can move towards their rain, but you got to be replacing the air that's coming in here. If it's moving this way, you got to really be getting fed good air from some direction. Where that wasn't the case with these, if they're moving, especially this way, they're moving away from where the inflow. So if this air was good and it's coming in this way and this way, it's moving away from that. So it's moving away from the inflow, and it's moving into the rain-cooled air. So the base, as the base gets more and more, it's just going to be fed junky air, except for whatever air up here is good that it's using back there. But you'll see another chase on here that the storm was kind of moving towards its inflow, but the low levels were really strong from the east, and it was vented really strong aloft too. But usually they want to be a little different motion than right towards where they're raining. They don't really last too long usually. Whereas you can see this one's propagating more towards the east and vented this way and inflow this way.